This presentation is on my independent technology study project for the 2015 to 2016 school year. This presentation will summarize the journey of my year-long project. In the interest of time, links have been provided to explain certain portions of this video in greater detail. To start off, please let me introduce myself and explain my background. My name is Colby Sakumoto. I am a senior at Mid-Pacific in Honolulu, Hawaii. In 2012, I started my freshman year of high school and became a member of its junior varsity air riflery team. Shooting and firearms have been an interest of mine since I first started playing airsoft when I was 10 years old. Air riflery allowed me to take the knowledge I had about shooting and apply it to a sanctioned high school sport. As of 2016, I have competed in 8 seasons of air riflery and claimed numerous awards for proficiency in marksmanship. I have also been lucky enough to be part of a team that has claimed 2 state championships in sporter air riflery. I was also the team captain and head gunsmith for the boys' varsity sporter and varsity precision air rifle teams. Aside from air riflery, I am a part-time employee at Hawaii's premier airsoft store, E-Power Sports. At this store, I am a technician who specializes in the repair and modifications of electric and gas-powered airsoft guns. Prior to 2015, I was an apprentice to the founder and owner of E-Power Sports. During this apprenticeship, I trained to be an airsoft gunsmith. I learned about basic Newtonian mechanics and how to apply them to airsoft guns to make them perform at their maximum potential. This experience has largely influenced my passion for gunsmithing. In my junior year, I was informed that an independent technology study would be offered to students in the 2015 to 2016 school year. I decided that this course option would be the perfect opportunity for me to combine several of my interests and use them in a way to fulfill a core class requirement. I wanted to study the technology of CNC machining and create accessories to use on the rifles used by the air riflery team. The main accessory I would be creating was a CNC aluminum precision stock for the Crosman Challenger Sporter rifle. In April of 2015, my project proposal for the class was approved with the condition that I would be allowed to pursue my project for 2 semesters due to its complexity. One aspect of competitive shooting, which inhibits its ability to be a more widespread sport, is the cost of equipment. In the United States, there are 2 types of 10-meter air rifle competitions, sporter and precision. In sporter air rifle, competitors must use air rifles that are approved by the Civilian Marksmanship Program, or CMP. These rifles are required to cost less than $525 US. Sporter air rifle was created to encourage youth participation in the shooting sports. It is for this reason that this particular shooting discipline requires competitors to use equipment that is considered to be affordable. In precision air rifle, competitors may use any air rifle they want with any aftermarket accessories they desire as long as the completed rifle fits within the sizing dimensions established by the CMP. Unlike sporter air rifle, there is no maximum price a competitor can spend on their rifle. Precision air rifle was created to encourage international participation in high-level competitive shooting. It was derived from precision small-bore rifle, an event at the Olympic Games. Currently, precision air rifle is also an event at the Olympic Games. Typically, a high school-age precision air rifle competitor will use an air rifle that costs about $1,600. However, they may use rifles that cost much more. The rifle I used during my high school precision air rifle career cost about $2,800. Most high schools that offer shooting as a sport can afford to equip a sporter air rifle team. However, they may struggle to afford the equipment that is necessary to compete in precision class air rifle competitions. Besides air rifles, there is a lot of other equipment that is necessary for rifle teams to purchase. This includes offhand stands, spotting scopes, ammunition, and in the case of precision class competitors, shooting suits. The objective of my project was to create a product that would allow high school rifle teams to use their Sporter class air rifles in both Sporter and precision class competitions. By eliminating the need for rifle teams to purchase a separate and more expensive air rifle for precision class competition, more high schools will be able to afford the other equipment that is necessary for a precision air rifle team. By increasing the ability to be part of a sanctioned precision shooting program, more individuals will have the opportunity to participate and experience the joy of an internationally recognized shooting sport. In Hawaii, the Hawaii High School Athletic Association, or HHSAA, hosts an annual state championship for Sporter class air rifle. Many competitors and coaches share the dream of having a state championship for precision class air rifle. However, the cost of properly equipping precision class competitors is a factor that is preventing this dream from becoming a reality. Enabling the commonly owned Crosman Challenger to compete with the more expensive European-made precision air rifles would allow more participation in precision class competition, and may allow the dream of a precision class state championship to finally be realized. I chose the Crosman Challenger as a base rifle for my project because it is one of the most widely used 10-meter air rifles among high school rifle teams across the United States. The Crosman Challenger features a Lowther-Walther barrel. This barrel enables the Crosman Challenger action, also known as the firing mechanism, to be as precise as a European-made precision air rifle. The Crosman Challenger stock, however, is not as adjustable as stocks found on the more expensive precision air rifles. This lack of adjustability will limit a competitor's ability to achieve an ideal shooting position and therefore decrease their ability to shoot with high precision. This is why my project was focused on creating a more adjustable stock. Having a precision-style stock will allow individuals to benefit from the precision of the Crosman Challenger action while being able to achieve an aiming position that is ideal for their shooting style. To get more information about the Crosman Challenger, please go to the link in the video description. During this project, I needed to work with several individuals who specialized in architectural design, engineering, and machining. This was because they had access to computer software and tools that I did not possess. Without these individuals, I would have not been able to complete this project. Working with these individuals was an amazing experience. Not only did they teach me about skills they use in their professions, they kept me inspired through the long course of this independent project. In May of 2015, I met with two architects to discuss the feasibility of my project. I explained to them the reasons for wanting to pursue a project that was a lot different from a normal high school assignment. After a long discussion about my background and project objectives, we began planning the necessary steps that would be required to complete this project. We created an estimated timeline and put together a list of resources that would be needed to be found in order for every component of the project to work. After the meeting, I began Phase 1. Over the summer, I collected the necessary hardware that was required for my project. This included a Challenger air rifle and several German-made rifle accessories that would be incorporated into the stock design. During the summer, I serviced and painted 16 of Mid-Pacific's Challenger air rifles. This process allowed me to become more familiar with the dimensions and inner workings of the current rifle design. It also allowed me to see some of the rifle's design flaws. I also purchased several books about competitive marksmanship-based shooting, as well as traditional and modern gunsmithing. These books taught me what to include in my project by teaching me about modern competitive shooting techniques and gave me several ideas for designs for my stock. In August of 2015, I arrived back at school from summer break. I had obtained 90% of the materials that would be needed to complete my project. I also had a much larger knowledge of firearm design and shooting styles from the books I had bought. Using my newly gained knowledge, I began drawing design concepts in my notebook. These designs varied in shape and style as they were all specifically designed to work with one of the shooting techniques talked about in the books. To make my decision on stock design easier, I created a survey for the Mid-Pacific Rifle team. In this survey, I asked basic questions about the participants' shooting habits and thoughts about the Challenger rifles. A link to the survey can be found in the description below. After I collected the surveys, I categorized each participant's answers and sorted them into various groups. After this process, I had decided on a design that would eventually become my final product. After deciding on a final design, I needed to create a 1-to-1 scale blueprint of the stock. When I created my blueprint, I used metric measurements. I chose to use metric units because the majority of aftermarket accessories that would be attached to the stock were made in Europe. Using millimeters, I used the electronic calipers to measure each component that would interact with the stock. These components included the Challenger action, cheek piece and butt plate clamping systems, accessory rails, and pistol grips. When determining where components were to be placed, I accounted for a tolerance of 0.001 of a millimeter. This was before I knew about the exact details of the machine mill my project would be created on. I also factored in clearances for components that could afford to have some amount of play without affecting the performance of the rifle. For components such as the Challenger action, I made the clearances on the stock slightly tighter. This was because I could not afford to have any play with the connection between the action and stock. The most difficult part of the measuring process was determining the measurements of the trigger box slot in the stock. This was because it involved aligning 7 different features that were very small in size. Also, I needed to convert a product made with standard measurements into metric measurements. An interesting note about my design is that it incorporates both American standard and metric measurements. Combining these two different measurement systems was unavoidable due to the fact that the Crossman action was made in the US and the Anschutz accessories were made in Germany. Combining two different measuring systems was not ideal, however, under the circumstances, it was unavoidable. After completing the 1-to-1 scale blueprint, it was time to start designing a CAD file. The word CAD is an acronym for Computer-Aided Design. Earlier in the year, I wrote a detailed report about the specific functions of AutoCAD and its applications in the fields of architecture and engineering. In short, AutoCAD helped me create a 2D digital blueprint of my design. I spent approximately 20 hours over the course of 6 weeks creating the CAD file with the assistance of Rosalind Chun, a project architect with the firm of Group 70 International. She has 28 years of architectural experience working on hospitality, educational, retail, high-rise residential, and office projects. At Group 70, she is responsible for the management of projects through design and the production of construction documents. Ms. Chun taught me about the basic controls of the AutoCAD 2014 software. The AutoCAD blueprint consisted of measurements from 6 sides of the rifle stock, including several enlarged images of areas that would require special attention during the machining process. The AutoCAD blueprint would eventually help me when I started creating a 3D model for the machining process. To read a more detailed report on what I learned during the AutoCAD phase of my project, please visit the link in the description below. After completing the AutoCAD file, the next phase of the project was converting the AutoCAD file into a 3D model. To do this, I would seek the assistance of Mr. Kaoru Levet, an architectural designer also with the firm of Group 70 International, where he specializes in brand strategies and project conceptual design. Mr. Levet is also a composite technician with the firm of Kumano Composites, where he was instrumental in designing carbon fiber freediving blades. He will also be attending the Harvard School of Design in the fall of 2016. There was a short break between the AutoCAD process and the 3D modeling process, as Mr. Levet was on the mainland to receive an award from the American Institute of Architects for a short film he and two other architects produced on architecture in Hawaii. During this time, I decided to embark on a side project to make productive use of my time. Because most of my main project involved computerized design and fabrication, I thought it would be interesting if I pursued a project that involved more traditional fabrication techniques. I also thought that a more traditional fabrication technique would allow me to further incorporate my gunsmithing skills in this project. I decided to modify the existing Crosman stock and make it better for precision class shooting. In order to do this, I used epoxy resin and fiberglass to reshape areas of the stock such as the grip and cheek piece. I also used lead weights to rebalance the front of the stock to compensate for the added weight in the rear of the stock. I used the design of the Anschutz 07 style stock as reference to tell me what parts of the Crosman stock needed to be modified. To read more about the process of my side project, please visit the link in the description below. In January of 2016, I was able to return to work on my main project. I spent approximately 20 hours working with Mr. Levet to input the AutoCAD file into Rhino, a 3D modeling software used by architects and engineers to create computer-generated renditions of objects they design. The Rhino software can be used to create 3D models before they are fabricated by a machine, such as a 3D printer or milling machine. The 3D model provides the fabrication machine with an object to create. From this point, the fabrication machine decides how it will create the object using its own programming. We began the 3D modeling process by importing the 2D design from the AutoCAD file. These drawings were assembled to create a 3D frame of what the stock looked like from 6 different sides. Once the frame was complete, we were able to begin creating solids, geometric shapes that represent objects with volume. These solids were used to fill in the measurements of the frame. When I was designing the stock, I kept in mind that the 3D modeling process worked using extruded solids. For this reason, much of my stock was based off of the shape of a rectangle. The most difficult part of the 3D modeling process was making sure that everything was aligned correctly. If any line was not aligned correctly, it would create problems during the machining process. Alignment of shapes was particularly important when we were modeling the slot for the trigger box. This was because the trigger box had the most amount of different measurements in the entire stock. When we were done creating portions of the 3D model, we would use the Boolean union command to make them an uneditable object. There were several design changes made to the stock during the process of 3D modeling. These design changes were made to the stock to make it easier and more affordable to machine. During the 3D modeling process, I learned the basic functions of how to use the Rhino software. Prior to using Rhino, I had experience using the SketchUp software. Rhino worked in a way similar to SketchUp. However, it allowed for more precise measuring and had more features. After we had completed the 3D model, I purchased a solid 1.5 by 1.5 by 44 inch 7075 aluminum blank that would be used to create the stock. I now needed to find a CNC machine shop. Finding a CNC machine shop that would be willing to accept a one-off project proved to be very difficult. On an island as small as Oahu, there are very few options when it comes to selecting a machinist. Luckily, with the help of Mr. Levet, we were able to find one of the best machinists in the state, Mr. Peter Sakumoto. Mr. Sakumoto is the founder and owner of Precision Machinery and Tooling LLC. He is one of the top CNC machinists in Hawaii. His excellent machine work can be seen throughout the state, including custom-made railings at major resorts and signage at major shopping centers in Hawaii. Other examples of his work include an IED search truck used in Iraq, a variety of parts used in industrial businesses, and numerous automotive parts. Precision Machinery and Tooling is located in the Pearl City Industrial Park and has over 15 CNC mills, lathes, and water jets. The company prides itself on its ability to turn customers' ideas into reality. Their machining services include everything from prototype development to large-scale commercial and government projects. Mr. Sakumoto was gracious enough not only to let me machine my one-off project at his shop, but to act as a mentor and teach me about the fundamentals of CNC machining. He and his wife stayed at their shop long after business hours so that I could work on my project, even when they were fulfilling large-scale commercial contracts for the government and other businesses. The name CNC is an acronym for Computer Numerical Control. A CNC machine mill is a computer-operated device that is used to precisely remove material from a workpiece. These machines are often used in fabrication industries. They have the ability to cut workpieces on an X, Y, and Z axis. They work by receiving a set of coordinates from a computer. These coordinates are created by finding the workpiece's location in relationship to the point of origin. The machine uses a rotary tool and bits to interact with the workpiece. Some of these bits include drills, end mills, and routers. Workpieces are secured to the mill with the use of the vise. These vices are anchored to a base that moves the workpiece around the rotary tool. Modern, computer-operated, industrial-grade machine mills, such as the one I would be using, cost tens to hundreds of thousands of dollars and weigh thousands of pounds. CNC machine mills have the ability to work with almost any material, as long as it fits within the machine's workspace and is not heavier than 600 pounds. During the machining process, we first started by uploading the 3D model into the modeling software that was compatible with the CNC machine. This software was a variation of Autodesk and functioned like most other 3D modeling programs. This process was more difficult than expected because my 3D model still had guidelines from the AutoCAD file that was built earlier. The guidelines needed to be deleted before the CNC received the coordinates it was supposed to machine. My 3D model was also made using metric measurements. The CNC I would be using operated using American Standard measurements. This meant that any adjustments made to the model from this point on would need to be converted into standard. Several alignment errors were also discovered while looking through the 3D model. These errors needed to be corrected before machining started. After several meetings discussing my 3D file with Mr. Sakumoto, several changes were made to the design to make the machining process easier. These changes included altering the way the butt plate carrier was anchored to the main chassis of the stock and the incorporation of an AR-15 style pistol grip adapter. Holes were tapped in the areas where screws were to be placed in order to make the threading process easier. When the 3D model was finalized, we began the machining process. The stock was to be machined in 3 different parts: the main chassis, the butt plate carrier mount, and the pistol grip mount. Because of the high strength characteristics of 70-75 aluminum, anchoring the stock together using steel screws would not compromise its structural integrity. The first part of the stock that was machined was the butt plate carrier mount. This section of the stock was machined from a 3.5-inch section of the aluminum blank. This section of the blank was cut using a bandsaw before it was placed on the mill. After the 3.5-inch block was secured at the origin point of the machine, the 3D model and machining coordinates of the carrier mount were sent to the mill. Before the mill started cutting into the aluminum block, we were able to watch a simulation of how the mill would move when making the cuts. After about 15 minutes, the top half of the carrier was machined out. The section of aluminum then needed to be turned upside down so that the machine could complete its cuts on the opposite side of the block. The same processes were taken to machine out the other side of the block. On this side of the block, however, special care was taken when the machine needed to use an end mill to cut 3 cylinders that would serve as anchors. When the machining process was complete, the unrefined section of stock was cleaned of oil and debris. A grinder was then used to dull and deburr its edges. It was a relief to finish this first section of the stock. At long last, I could see that my invention was becoming a reality. However, this was only the first step. Much more work would still be required. I left the machine shop that night at 11 o'clock. My next visit to the shop occurred 2 weeks later. I was determined to finish the machining process during this visit. I would be machining the largest section of the stock, the main chassis. Like the carrier mount, the main chassis was separated into its own file with its own coordinate instructions. A 30-inch aluminum block was cut for the main chassis. As with the prior component, the aluminum block was centered at the origin point of the machine. The aluminum block would need to be flipped during the machining process to create the underside of the stock. There was a lot of careful measuring that had to be done when submitting the coordinate instructions to the mill. This was because the rifle's barreled action was to be bedded in the chassis. The top side of the main chassis was the first side of the aluminum block that was machined. A large end mill was required to create the channel that the rifle's action would sit in. In order to do this, it needed to remove a massive amount of material from the top half of the block. When the aluminum block was flipped to machine the underside of the stock, a similar size end mill was required to create the channel for the accessory rail. Next, another end mill was used to create the contour on the rear of the stock. A few adjustments needed to be made to the main chassis after testing the fitment of the action. Luckily, these adjustments were easy to make. After the main chassis was complete, the pistol grip adapter was machined. Because this part was very small in size, it only took about 15 minutes to machine. Now that each component was machined, it was time to assemble the stock. A manually operated milling machine was used in this process. Due to the size limitations of the CNC mill, there were 3 anchoring holes that needed to be made in order to attach the carrier mount. A vise was used to hold the main chassis in an upright position so that the anchoring holes could be tapped. A tap was used to give the holes threading. The tapping process required a lot of force due to the strength of the 7075 aluminum. After the stock was assembled came the moment of truth. I screwed in the barrel action of the Crosman Challenger and attached the aftermarket accessories. The hardest part of my project was complete. The stock could not have turned out better. Words cannot describe how satisfying it was to hold the completed rifle for the first time. I left the machine shop at 2:30 in the morning. Now that the rifle was complete, I could start the process of fine-tuning and refinement. Although the CNC mill performed a finishing pass after each cut, the finish of the completed aluminum stock left much to be desired. It suffered scratches from machining debris as well as stains from oil. I used different grades of sandpaper to remove most of the shallow scratches. These grades of sandpaper started at 100 and went all the way up to 3000. An aluminum polish was used to give the stock a brilliant shiny finish, as well as to protect it against rust. Parts of the Challenger action were polished using the same technique. I modified several mil-spec AR-15 pistol grips to use on this rifle. These grips were tailored towards the dexterity of a user. The finishings and accessories I created for my stock are just a few examples of what my creation is capable of supporting. There are an endless amount of modifications that can be made to this stock. The accessories attached to the rifle in the pictures are examples of what I would suggest using in a 10-meter air rifle competition. Now that the project is officially complete, I look back at the long journey and smile. To me, this project was more than just an assignment for school. It was the fulfillment of a childhood dream and a first step into my future. Without the assistance of Rosalind Chun, Kaoru Levet, and Peter Sakumoto, this project would not have been possible. I cannot thank them enough for their patience in mentoring me and for being so generous with their time. Working on this project and getting to meet some amazing people has made my senior year a truly memorable experience. Finally, I'd like to thank my father for supporting me throughout this entire project. Thank you for driving me to all of the faraway locations, for taking time out of your busy work schedule, for filming me throughout this project, and for spending thousands of dollars on supplies. This project would not have been possible without your support. Thank you for watching my presentation.